In the next several examples, we want to take a look at this process for optimizing a multivariable function from beginning to end, finding all the appropriate derivative functions, evaluating those, and then testing each point using that second derivative test. In example 5, we'll start off by finding f sub x and f sub y, the two first partial derivatives, which in this case would be 6x minus 4, and f sub y will be 4y. In part B, we want to find all critical values, meaning we want to take our first partial derivatives, set equal to 0, and solve. In this case, we'll get x is equal to 2/3, y is equal to 0, meaning we have a single critical value at 2/3, 0. Next, we need to find all of the second partial derivatives, meaning we need to find f sub xx, which will be 6, and f sub xy, which will be the derivative of 6x minus 4 with respect to y, so we'll get 0. We need f sub yy, which will be 4, and f sub yx, which will be the derivative of 4y with respect to x, and so we get 0. Then to calculate that value for d, we'll take 6 times 4 minus 0 times 0, and we'll get 24, which is greater than 0. That means we either have a local maximum or a local minimum, so we check f sub xx, which is equal to 6, which is also greater than 0, which tells us that 2/3, 0 is a local minimum. In example 6, we have the same process. We'll start off by finding g sub x, which will be negative y plus 10x minus 5, and g sub y, which will be negative x minus 1. We take each of those first partial derivatives, set them equal to 0, and solve. In this case, it's much easier to solve minus x minus 1 is equal to 0. That will give us x is equal to negative 1. And we want to do that first because then this other equation that has two variables, we can substitute in x equals negative 1 to get it down to just a single variable, and then solve negative y minus 15 is equal to 0, or we get y is equal to negative 15. So we have a single critical value again, in this case at negative 1, negative 15. We find each of our second derivative functions, which will give us g sub xx will be 10, g sub xy will be negative 1, g sub yy will be 0, and g sub yx will be negative 1. And then we calculate d by taking 10 times 0 minus negative 1 times negative 1 will end up giving us negative 1, which is less than 0. Since our value for d is less than 0, then we know that this function has a saddle point, so neither a maximum nor a minimum, at negative 1, negative 15.